algebraic manipulations as well as identities. Um, so if you guys remember last time, we covered this identity, which was very, as I mentioned, very important. It was the um, x plus y times x minus y equals x squared minus y squared identity. And as you guys know, like if you expand the product out, you guys are gonna get this identity. And as you saw, we can use this kind of symmetry to exploit really a lot of situations in problems. Um, so today, through this problem, we'll explore another type of identity that is also very frequent and common hold in math competitions, and something that you guys should um, I mean, you guys should know how to do it, but I think you guys should memorize it as well, just because it saves some extra time. If you like, it just saves some extra time that you can like avoid, because in these competitions you're really rushed for time. So if you can save some extra time, then that's going to be useful. Um, and so it says that let x and y be real numbers such that x plus y equals 5 and xy equals 3. So we want to find the value of x squared plus y squared, right? So what do I see here? I see a squared here and I see a squared here. So that immediately makes me think about like squaring this expression and doing something with it, right? Because I wanna, because it says x squared plus y squared, and I'm gonna see if I can square this expression get and then get something, and then get like the sum of two different squares such as x squared and y squared. So I'm gonna try squaring that equation. So I'm just gonna say x plus y equals 5, and then x plus y squared equals 5 squared, right? So we kind of just square both sides of the equality, right? And um, so 5 squared is 25, and that's easy. But what we have to do is we have to expand this side right here. And so x plus y squared is actually going to be x plus y times x plus y, right? It kind of looks similar to this, except that this x minus y is now an x plus y, right? So the way you can uh, the way you can try expanding this expression is if you oh, yeah, so the way you can try expanding this equation is obviously uh, just by doing it part by part. So you can take this x, for example, and then you can multiply the x by this first x and get x squared, and then add, and then yeah, and then you can multiply the x and the y here. So if we focus on this x, we have to multiply it by this x, and then we have to multiply it by this y as well. So if you do it part by part, you can see that x squared plus xy, and if you do the same thing for y, you get something like yx plus y squared. And since these two terms are equal, we can say that that's actually equal to x squared plus 2xy plus y squared, right? And so now we see that yes, indeed there is um so that you can do something with x plus y such that it yields some form of the sum of two different squares. And so x plus y squared is going to be x squared plus 2xy plus y squared, right? And so we can say that x squared plus, oh, my pen, yeah, so x squared plus 2xy plus y squared is going to be 25, right? And so from here we can see that um, we want to find x squared plus y squared. So we need to do, so if you want to solve for x squared plus y squared, we can see that that's equal to, if you subtract 2xy on both sides, you get something like this. Oh, I'll just make it more, just make it neater. right? So, right. And so now you can see that 2xy, actually the value of xy is given here, right? So the value of 2xy is going to be 2 times 3, right? Which is 6. And then if you subtract the 6 from here, so you get x squared plus y squared equals 25 minus 6, which is 19, right? Um, so the answer we want and this problem is 19. But I think getting to the answer is fine, but like I think the main idea we were trying to see here is that x plus y squared is going to be x squared plus 2xy plus y squared, right? So this is like a very important kind of identity that you might want to know, right, moving forward. um expanding it all the time requires a lot of time that you don't kind of want to waste in competitions. I mean, it's fine, but like you if you remember this, you'll obviously save the extra time and solve the problem. And so while we're at it, I'll just mention the identity for x minus y squared as well. It's going to be x squared minus 2xy plus y squared. So x plus y squared is going to be x squared plus 2xy plus y squared, and then x minus y squared is going to be x squared minus 2xy plus y squared. And I encourage you guys to like try this identity at home, like expanding it and seeing that it actually works out. But I'm not going to do it here just for the sake of time. And so um, using kind of this identity, we will try tackling this problem, which says suppose x is a real number such that x plus 1 over x equals square root 2013. And so we want to find x squared plus 1 over x squared. So before I start solving this problem, does anyone have any ideas on how we can kind of approach this problem? No ideas. All right. So again, we see the sum of two different squares. So we see the sum of x squared and 1 over x squared, and we kind of want to find um, the sum of these two squares, right? So again, squaring this expression. I'll try squaring this expression to see if that leads us somewhere. Just simply because we saw that squaring the expression uh like led to us finding the sum of two different squares the last time we did such a type of problem, right? Just now that you guys see that there's no xy, or there's no product of the two different quantities given, but as we'll see in this problem, we won't end up needing that at the end. So x plus 1 over x squared equals square root 2013 squared. And we know that this is going to be 2013, right? Because square root 2013 squared is going to be 2013. But help me expand, or help me find um, this quantity. What do you guys think it is? What do you guys think it should be? All right. Um. So, uh, so again, right? X plus y squared is going to be x squared plus 2xy plus y squared, right? And we can kind of see that this expression and this expression kind of looks like the same thing, except if y equals 1 over x. and say y equals 1 over x, we find that x plus 1 over x squared is going to give us x squared plus 2x times y, but y is 1 over x, so 1 over x plus 1 over x squared, right? And what's 2x times 1 over x? Is just 2, right? So it's x squared plus 2 plus 1 over x squared. And now, as you guys can see, we didn't actually, like the problem didn't specify like the product of two different quantities, but we didn't end up needing that anyways, because basically what we're doing is we're adding two reciprocals. And so if you're adding two reciprocals, because x and 1 over x are reciprocals, right? So if we're adding two reciprocals and squaring them, the x squared and the x squared and the y squared term will be fine. It's just x squared plus 1 over x squared. But the 2xy term in the middle, 2x, but then y now is actually 1 over x, right? And so if you're multiplying two reciprocals, that's just 1. So x times y is just y, just turns out to be 1. And so the product of the two terms is just 1, right? And so the actual expression turns out to be x squared plus 2 plus 1 over x squared. So we didn't really actually need the product of anything in this problem. We needed it for the last problem because x and y are two different variables, so they have nothing to do with each other basically. And so substituting this expression back here, we get this, right? Because this is what we got for uh, x plus 1 over x squared, and now we can see that, right? Because just if you just subtract 2 on both sides, you get 2011. So again, like this just goes to show how prevalent these types of this identity is, and it's also important to remember the x minus y squared identity. These identities are really important moving forward, right? So um so now let's look at this problem, which says um that x y be real numbers such that x plus y equals 7 and xy equals -2. And so what is the value of x cubed plus y cubed? Um, so this problem is a bit on the harder side because we haven't really looked at cubic functions yet, but I think this is also an identity that you guys should know, especially like in the AMC and moving forward, because it just shows up a lot. It just shows up everywhere, right? So it says x plus y equals 7 and xy equals -2. So what's the value of x cubed plus y cubed? And so we know that if this was x squared plus y squared, we would have found it, found the expression, right? It's easy using the above identities. But now we don't really have an identity establishing anything for cubic functions yet. And so what we can try doing again is just cubing this expression and see if that leads us somewhere, right? Because I mean that's the only way we can proceed right now is that I see the sum of two different cubes. I'm just gonna try cubing x plus y equals 7 because obviously in the earlier problems as well, we wanted to find x squared plus y squared. Obviously, squaring x plus y led us somewhere, right? So I'm gonna try the same thing here, and I'm gonna try cubing this expression. So cubing both sides of the expression. Um, and just so 7 cubed is just 343, right? I mean you can pull out a calculator and do this, or you can just do mental math in your head. But we want to find this expression now, x plus y cubed. Well, we see that x plus y cubed, you could obviously, you could obviously um, just try multiplying x plus y times x plus y times x plus y, right? And then go through all that. But you could also do something clever here, which is the fact that if you use kind of the knowledge that we gained before um, about the product of product of two sums, right? Like x plus y squared, right? So if we square two sums, we know that's going to lead us to x squared plus 2xy plus y squared. And so I can actually skip a step and say x squared plus 2xy plus y squared times x plus y. Because this is just going to lead us to this. And so we can kind of backtrack that way. And so we see that now, obviously, we have to do the multiplication. It says x cubed, right? So just focus on the x squared and then multiply it with x and y on the other side. So x squared plus x squared y. And then we focus on the 2xy. So 2x squared y plus 2xy squared, right? And then we focus on the y squared. And the y squared is going to give us y squared x plus y cubed, right? And so we can see that we have x cubed plus y cubed like we want in this function. But now we see that we have all these extra terms, extra four terms as well. Well, if we see these extra kind of four terms, we didn't really have to deal with this in the other expressions, but I would try seeing if you can combine these four into like some smaller amount of terms. And so we see that we can indeed do that because um, 2xy squared plus y squared x is going to give us 3xy squared, right? This is going to give us 3xy squared. And x squared y plus 2, oh, I'll just erase this. Yeah. And this is going to give us 3x squared y. And you can kind of add these two expressions. And so, I mean, obviously simplifying, because we see that we can factor out some terms that's going to be easier for us moving forward. I'm just going to factor this. I'm just going to bring out the 3 and the xy because it's common in this expression, it's common in both terms. And we see that 3xy, we can break this up into 3xy times x plus y. So our actual expression is x cubed plus 3xy times x plus y plus y cubed. And that's what x plus y cubed equals 7 cubed is. And now we see that we actually have all the quantities that we need to solve this problem because we want x cubed plus y cubed. So we have x cubed plus y cubed, and that equals 343. But we have to get rid of this little term, right? So we can say x cubed plus y cubed equals 343 minus 3xy times x plus y, right? Just subtract this term from both sides. And we can see that this term, we have xy is given to be negative 2. So negative 3 times negative 2 is going to be a positive 6. And then times x plus y, we are given x plus y as being 7, right? So that's 7, right? So that's 42, right? Negative 3 times negative 2 times 7 is going to be 42. So since I already took care of the negative 3 here, the actual product is going to be 343 plus 42. And that's going to turn out to be 385. And yeah, so this problem again, obviously getting to the answer was one of the parts of the problem, but like the most important thing about this problem is realizing or coming up with the identity that x plus y cubed is going to give you x plus y squared x my bad it's going to give you x cubed plus y cubed plus 3xy times x plus y. And so this identity also shows up in a lot of places, and it's useful to remember, right? And but so while we're at it, I'll just cover one more identity, and I'll actually um, go over the steps, or go over like how to come up with the identity as well. So I'll go over the x minus y cubed identity, because just because like it comes hand in a hand with x plus y cubed. So that this identity, it's gonna be, so we can again, right, just break it up into x minus y squared times x minus y. And by doing this, we can see that x minus y squared is going to be x squared minus 2xy plus y squared. Remember, x squared minus x minus y squared and x plus y squared, it's basically the same thing, just that the 2xy in the x plus y squared, it becomes a positive, but then in the x minus y squared, it becomes a negative. It's easy to remember as well, because positive and positive goes together, and negative goes together, right? So um that's good. That's kind of what's, well, like the expansion is going to look like. And then we can actually um kind of expand this product out even more, and we can say that it's x cubed. um so x cubed minus x squared y, so just focusing on the x squared, and then minus, oh, yeah, and then uh so we're going to just focus on the negative 2xy, so we're going to get negative 2x squared y plus 2xy squared, right? Because it became a plus, because negative 2xy times negative y is going to be plus 2xy squared, and then plus y squared x minus y cubed, right? So the product is actually going to be x cubed minus y cubed, and again, grouping these things together, we can see that negative x squared minus negative x squared y minus 2x squared y is going to give us negative 3x squared y, and then a positive 3xy squared, as you can see by grouping these two expressions together. And then we can obviously distribute to make our identity kind of simpler looking, and we're going to see that if we factor out the negative 3xy, um, we're going to get, and so this is what x minus y cubed will look like, right? So looking at these two boxed identities, which is this one and this one, notice the similarities and differences, right? So it's actually gonna help you guys, or wait, I actually made a mistake here. Yeah, right. So it's actually gonna help you guys remember this. So first of all, we can see that x cubed plus y cubed and x cubed minus y cubed, right? So we can kind of spot the difference here. Obviously, it's pretty evident, because if you multiply negative y 3 times, you're gonna get a negative y cubed, right? So x cubed minus y cubed, and then this positive 3xy will become negative 3xy, and then this parentheses expression is whatever is in the parentheses here. So we can see the x plus y is in the parentheses there, so this is going to be x plus y, and then this was in the parentheses here, so this is negative. This is x minus y, and yeah, I guess it's just a way to remember these two identities. Obviously, it'll help if you remember these two identities, right? And I think so. There is actually this identity which is called the sum of two cubes, and so which was so there is actually an identity for this, um which I can cover, and then yeah, we'll see if you have time for the difference of two cubes, and if not, then Daniel will obviously take over that. So, if we have the sum of two cubes, x cubed plus y cubed, can someone help me get to what this identity could be, or suggest next steps for um doing something like coming up with this identity? It's actually very derivable from some of the things we have here. All right. So, I mean, first of all, you could notice that this is just going to be our x plus y cubed expression, right? Because we said that x plus y cubed is going to be x cubed plus y cubed plus 3xy times x plus y, right? But um, so we want the first two expressions. We want the first two terms of this expression, and we kind of want to avoid this term. And so so if this is a positive 3xy times x plus y, what do you think I should do with to avoid this term, right? We can just subtract the same thing, right? So so our x plus y cubed expression is going to give us x cubed plus y cubed plus this term, right? This term, and then what we can do to get rid of this term is, because this is a positive, we can just basically subtract the same amount, right? And the term is going to cancel out to become 0. So x cubed plus y cubed is going to be x. Uh, so now that we've established this, uh, we can actually see that we can make this expression a lot more simpler, right? So if we want to do that, we get x plus y times x plus y squared minus 3xy, right? And so x cubed plus y cubed is going to be um, x plus y. So we can factor out the x plus y from both equations, and we see that that's x plus y squared, which is x squared plus 2xy, and then the minus 3xy from the second term. And so what we kind of did here is we saw that x plus y is common in both terms, and so we distributed that out, and we combined the other two terms that resulted from the breaking of the x plus y term, right? So, and then this term is going to be x plus y times x squared minus xy plus y squared, right? And so this is what we call the sum of cubes. And so whenever you want to find the sum of cubes, or whenever you're asked to find the sum of cubes of two expressions in the AMC or in the SAT as well, sometimes um, you just find the sum of you just find the sum of the individual terms of the cube terms. So you have to find the sum of the two cube terms. You find the individual terms, and then you basically just find the sum of the two squares of those terms, right? So x squared plus y squared, and then you subtract the product from them, and you just multiply these two expressions. Uh, that looks like an yeah. I'll just yeah, right. And that's the identity. It's a very important identity to know. It's a identity for the sum of cubes expression. And so with that, I'm gonna hand it over to Daniel, who go over the sum of the difference of two cubes, and then uh, move on to quadratics.
All right, cool. Well, hi everyone. I'll be finishing up the session with algebraic manipulations, and also we'll be starting quadratics, which actually won't be covered very often on the AMC. Although it would be good to know in case you're taking the AMC 10 or 12 in the future, or if you happen to like or most of you are going to take the SAT or ACT. So the concept of like quadratics and factoring quadratics and tactics such as like Vieta's formulas will most likely pop up on the SAT too. So those are very important to know. And even though they won't be very frequent on the MC, um, it's just a good concept to know in advance once you get to like the harder competitions as well as standardized tests. So let's get started. Um, with finishing up our special factorizations that Sid talked about. So in our derivation above here, we basically derived an expression for the sum of cubes. So namely, x cubed plus y cubed. And we saw that the sum of cubes factorization, uh, x cubed plus y cubed, can be written as the product of two separate terms, which are namely x plus y and x squared minus xy plus y squared. So we just call that the sum of cubes, or just sum of cubes factorization. We also have another one, which is basically the same as, which is basically the same as sum of cubes, except that we incorporate a little negative there. So what I mean is that if you want to let's consider the term x cubed minus y cubed. Adjust the thickness a little bit. Scrolling. All right, so x cubed minus y cubed. And this is actually very significant because we call this factorization the difference of cubes. And it's basically the same thing as sum of cubes. Because if we want to know how we can factorize x cubed minus y cubed, we can actually just replace uh, all instances of y with, let's say, another variable like z, right? So the substitution we will want to make here is y equals negative z. And so um, let's start off with our known sum of cubes, which is x cubed plus y cubed. And then writing that out, it is x cubed plus y cubed equals x plus y times x squared minus xy plus y squared. And then now let's bring in our factorization, which is y equals negative z. And we'll see why like naming another variable z is helpful in our situation for finding the factorization for x cubed minus y cubed. So let's substitute our new variable negative z in for y. So when we do that, we get x cubed plus y, which is negative z cubed, equals x plus y, so which is just plus negative z, times x squared minus x times uh, negative z, because y is, again, we're substituting negative z in for y, and negative z squared at the end of the expression. So now let's just simplify this expression a little bit, clear things up. We'll get x cubed minus z cubed equals x minus z times x squared plus xz plus z squared. And with that, this is our difference of cubes factorization. So whenever we like spot a sum of cubes, like x cubed plus y cubed, or if we spot x cubed minus z cubed, we can immediately think of these two factorizations over here in order to simplify this expression a little bit. Often factoring is a very useful tactic for just simplifying algebraic expressions. And if like the terms like don't seem to be very nice, if the especially like if you're dealing with like very very big numbers, but you see like the numbers are like cubes, like let's say like you get something like 4 to the ninth, right? You can write 4 to the ninth as like 4 cubed cubed, which will give you 4 to the ninth by exponent rules. And if you're summing that up with another number such as like 1, right? One, you can write it as like 1 to the anything power. So 1 to the so you can write in that case you can write 1 to the ninth, which is 1 cubed cubed. And then from there you can write you can basically force sum of cubes into that expression, and then you can factor it. If you're asked to find like the prime factorization or how many prime factors it has, you can obviously use those two factorizations to help. So it's very useful when we like find like two cubes that are sum or differences of each other, and from that we can just factor the expression. All right, so those are very two useful ones. I'm gonna give you like I'm gonna show you what I mean by finding like the sum of cubes. And this is like an example I just thought of in my head, but we'll see like how it can help. So if you're like uh if you let's say you wanna find like the biggest prime factor of 4 to the 6 plus 1, right? So let's write that down. 4 to the 6 plus 1. And remember what I mentioned earlier about like forcing cubes into that expression. Remember that the exponent here, right here, with 4 as the base, is like divisible by 3, because 6 equals 2 times 3. And with that knowledge, we can actually write this expression as 4 squared cubed plus 1 cubed. And remember that 1 to the anything is basically just 1. So uh, 1 cubed will be just 1. We won't be changing the expression at all. We'll just be rewriting 1 as a cubed so that we can apply sum of cubes to this expression. So let's apply that sum of cubes factorization to this. So when we do, remember that x cubed plus y cubed equals x plus y times x squared minus xy plus y squared. And then you get, so we can actually just substitute in x equals 4 squared, y equals 1. And then substituting these values into our factorization underlined at the right will give us 4 squared plus 1 times 4 squared squared minus 4 squared times 1, which is just 4 squared, and then plus 1 squared, which is just 1. And then with that, you can just clear things up a little bit. 4 squared plus 1 is 16 plus 17, which is 16 plus 1, sorry, which is 17. 4 squared squared is 4 to the 4th minus 4 squared plus 1. And then we can write 4 squared as, well, actually it could have simplified here, but basically 16 squared, which turns out to be 256 minus 16 plus 1. And then 17, you get 17 times 256 minus 16 is 240, and add another 1 to get 241. I believe like 241 is it prime? I'll just quickly check. Yeah. So 241 is prime. That's our biggest factor. We can obviously like check with other number theory tactics, which we'll be covering in our later sessions throughout the month of December. So that's like a really nice application of sum of cubes, right? Just like noticing that the the exponent 6 is divisible by 3, which we can kind of like write 40 to 6 as a cube. And noticing that 1 can be written as like 1 to the any power. So in that case, it's kind of like a perfect power, right? Like 1 can be written as a square, as a cube, as like a fourth. It can be written as anything. So like 1 is like a really nice number for factoring these types of expressions. All right. So that was a like short but nice example of like factoring with sum of cubes. And obviously you can use difference of cubes in similar situations. Like if this plus was instead of like a minus, then you can obviously use difference of cubes to tackle this problem. But yeah, that you'll see like difference of Qs and sum of Qs a lot in like in the AMC 10 and AMC 12. Not so much in the SAT or ACT, but uh, those are like very nice to know. And like who knows, like maybe like the AMCs have been like adding a lot of like quirky ideas on their tests recently, especially like on the AMC 10 and AMC 12. So who knows if one day they'll add like a sum of cubes or a difference of cubes on the AMC 8 one day. So you never know. It's just good to know. More knowledge is, is better. So uh, let's let's cover this one last problem with algebraic manipulations. So it asks for solve for triples ABC of integers such that AB equals 30, BC equals 12, and AC equals 10. All right, so does anyone have any ideas about how we can approach this problem? Well, for this problem, right, you have three products of integers. Um, and like as we obviously like covered like sum of cubes and difference of cubes, but there doesn't like seem to be like any like cubing or anything like that. So it doesn't seem like sum of cubes or difference of cubes will help us here. Um, is there anything interesting about this problem? Like sometimes like maybe remember like the tactics that we covered in our earlier sessions, like substitution, elimination. Sometimes like spotting like symmetry will help. Well, let's look at these expressions one more time. So I'm just going to read it one more time. So for triples ABC of integers such that AB equals 30, BC equals 12, and AC equals 10. It's kind of interesting here because like if you look at each of these three equations, you get that the like the left-hand sides are always products of two distinct like variables. So two different variables like AB, BC, and AC. And it is also interesting because like all three pairs of the variables are like chosen. So like um, if you want to form like a list of all possible pairs, like pairs of uh, distinct variables, right? So this is like these three are like the variables here, right? You can write it. You can write like a b and then a c and then b c when we do the last two. So we get all three possible pairs of integers. So that looks like kind of symmetric to me because it's kind of like in the same form, if you know what I mean, like two variables multiplied at the same time. So is there any way we can like use the symmetry to possibly help us form an intermediate like equation? And let's actually think about like if we have any like similar problems to this one, right? I don't know if we have a good example here. Let me try to find one. These are above our proportions. We didn't cover those yet. I I was thinking of a possible problem. I don't know if you guys have done this, but if you have like instead of a multiplied by b, like if you have solved something like these, which maybe we should have like covered as like a preliminary example, because this is basically like almost like the same thing. If you have like a plus b equals 30, like if instead of multiplication you have addition, like a useful tactic would be to add all three of these equations, and that'll give us like two, because we have two a's here, two times a, and in two b's and two c's, so two times a plus b plus c, and then you get the sum here, and then we can obviously uh, that will like help us dramatically. So with that in mind, uh, uh, let's like try to exploit this symmetry by like multiplying all three of these equations. It's kind of annoying. All right, let's erase this, and let's like use the let's try to combine these three expressions, because what's very useful in problems involving symmetry is that like when you add, subtract, multiply, or divide uh, like all of these equations, you will will eventually get like an intermediate equation that can help us like solve for the values of a, b, and c. So that's actually I'll show you what I mean and connect this back to the addition problem when I'm done. So let's multiply all of them. So let's we'll get uh, again we have two a's, right? There's no a in the middle equation. Uh, that which will produce a squared, and same with b, because there's no b in the last equation, which is b squared. Same with c. So it's a squared times b squared times c squared on the left hand side. That will be the product of the three numbers given. So that will be 30 times 12 times 10. Right. And then note that like a, b, c are integers. So let's like try to rewrite this a little bit. So if you write 3 times 10, which is 30, and 2 squared times 3, which is 12, and 2 times 5. Or actually, we can just leave it as 10. That would be a lot easier. So if we write it like that, we can actually see how it's like really nice here, because if we just multiply the like terms together, right? So 2 squared, because there's only one 2 in the middle, and you get two threes, right? Two threes, which is 3 squared and 10 squared, because there are two tens, one in the 30 and one in the 10, if that makes sense. Basic because 10 divides 30, 10 divides 10. Same thing as saying 30 is divisible by 10, 10 is divisible by 10. So that's why you get 10 squared, or just like two 10s multiplied by each other. And you get a squared times b squared times c squared. And then taking the square root, now this is where you got to be careful, because when you take the square root of both sides, uh, and like the right hand side is an integer, right? It's something, it's a value that we know. We must include the positive and the negative value. So to make it more clear, I'm just going to write it as abc squared um, equals 2 squared times 3 squared times 10 squared. So it's taking the square root of both sides gives plus or minus 10, 2 times 3 times 10. And then which is 2 times 3 times 10 is 2 times 3, which is 6. 6 times 10 is 60. So A, B, C is plus or minus 60. This symbol right here basically denotes like there's a positive solution or a negative solution. So like saying ABC equals plus or minus 60 is equivalent to saying ABC equals 60, positive 60, and or actually ABC equals negative 60, because you can't have like ABC equals 60 and negative 60, right? They can't, like ABC can't hold two values at once. It's one variable. It's like kind of like one variable. So basically this is like it. This is very important because like when you go from this step over here to this step over here, you must include the plus or minus sign in front of the constant, because uh, when you have something squared, uh, there it can be positive or negative. Uh, that can lead to the constant on the right hand side. So here, like it's kind of like saying like negative 60 squared, right? Is that will give us 2 squared times 3 squared times 10 squared, and then 60 squared, which will also give us that. And like this this is kind of explains why like we need the plus or minus, because the positive solution and a negative solution can both work. And so now the problem is basically finished, because with ABC equals 60, which was what I was referring to as the intermediate equation, we can divide all of these equations to get like ABC. So if you start off with ABC equals 60 and divide by this equation, right? Divide by AB and divide by 30. We can do this because AB and 30 basically are the same. You're dividing by the same number on both sides, which is why we can do that. So AB cancels out. You get C equals 2. Do the same thing. Um, AB, I'll actually skip over kind of like most of the details, but you should get um, B equals, well, actually, like C equals 2. You can actually plug this back into BC equals 12. So B times C, which is B times 2 equals 12. So you're doubling B to get 12, which is 6. And then again, you can substitute C into the third equation right over here, and you should get A equals 5. So that's one solution. The other solution, ABC equals negative 60 for our intermediate equation, should yield all negatives. So C equals negative 5, B equals negative 6, and A equals C equals negative 2. C equals negative 2, I mean. B equals negative 6, and A equals negative 5. So our two solutions will be uh, A, which is 5, B, which is 6, C equals 2. It's very important that you don't mix all like these cases up when you're doing the problem. And then like don't do it as like messy as I did over here. You should ideally do all of like the substitution and like all of the work like underneath one equation, and just to kind of like split your work up so that your it's just like more organized to follow the numbers around. So you get 562 and negative 562 as our two solutions for our triple ABC. So these two are our solutions. Now let's like make one more connection before we close the session off, to our like addition problem, right? So what I was like mentioning with this problem is that a like let's replace all these multiplications with addition, right? So a plus b equals 30, um, bc equals 12, and ac equals 10. A plus c, a plus c equals 10. I mean, sorry. So rather than multiplying all of these equations, we can add all of these equations. So as I mentioned earlier, you should get 2 times a plus b plus c, because you get 2 of each variable on the left-hand side. And that will give us 52. And then the intermediate equation is a plus b plus c equals 26. Now remember, it's not negative 26 because we're just dividing up by 2 on both sides. We're not taking like the square root of anything. So that's why we only get one possible intermediate equation. And then what do we do with this intermediate equation? Well, we can basically do like the same thing that we did, almost the same thing that we did above, right? Let's write this intermediate equation down. A plus b plus c equals 26, just like we did with our with abc equals 60 right over here, right? So I'm gonna trace this in purple so that you can see the connection here. So abc equals 60, a plus b plus c equals 26, and let's write the first equation down to solve for c. So a plus b equals 30. And then what we do is that we subtract. Depends a little bit. So we subtract a plus b from the intermediate equation to get our value of c equals negative 4. And then look at the connection here. We basically took our intermediate equation and then divided that intermediate equation by one of our given equations, and then that basically gave us one of our values for the variable. And yeah, so we kind of ran out of time for quadratic equations, so we'll be covering that next week. And hopefully you enjoyed the section, learned something new. And thank you very much for attending. We'll be sending out a recap email for the problem set, and as well as for
Yeah.
next week's session, as well as the recording too.
All right. Thank you guys. Bye.
So thank you very much for attending, and we'll be covering quadratic equations next week. So see you then.